Good. Okay, great. The recording's going. Hello and welcome to this session on the ARKIVUM solution for ARCHIVER. I'm Matthew Addis. I'm the ARKIVUM's Chief Technology Officer, and I've led ARKIVUM's work in the ARCHIVER project during all three phases of ARCHIVER. And I'm going to take you through our solution today and show you in some detail what it can do. Session is scheduled to be 3 hours long, but I'm expecting we'll be done before then. I've got just over 2 hours of material that I would like to present. That's a mix of slides and demonstrations. The agenda for today's session starts off with a brief overview of ARKIVUM as an organization and the products and services we offer. I'll then give a high-level overview of our ARCHIVER solution. So the first part of the session will take about 30 minutes, and it's somewhat similar to the content presented at the ARCHIVER public event last Monday. So apologies if you attended that event, but I wanted to make sure that this webinar is self-contained and sets out the context of our solution before I go into the details. The majority of today's session will be a detailed set of presentations and demonstrations of our solution. And I've split that into 3 parts of about 30 to 40 minutes each. So there's about 2 hours of content in total. Almost half of that will be demonstrations, so you'll get to see a lot of the ARKIVUM solution working in practice. I'm proposing a 5-minute break in the middle, so everyone can sort of refresh themselves and get a drink, etc. at half time, and then we'll take questions at the end, and there'll be plenty of time for that. And that helps make the recording of the webinar be as compact as possible for people who couldn't make it today. So normally I've allocated 30 minutes for question and answers, but there's time to talk for up to an hour if there's lots of topics to discuss. Session, as you know, is being recorded, but we'll also make the slides available too. And the demonstrations that I'll show, I have recorded those in advance, and there are videos that include a narrative, so we'll get those up online as well. So all of that means you don't have to worry about taking notes, and if you want to do things like do a few emails whilst I'm talking, then that's fine with me too. So first of all, a few words about ARKIVUM and our involvement in ARCHIVER. So a quick overview of ARKIVUM. I'll talk about our products and services, mention of certification standards and good practice, our approach to ARCHIVER, the partnership we have with Google, and the availability of the solution that I'll go on to present through EOSC. So for those of you who don't know much about ARKIVUM, we were founded a little over 10 years ago as a spin out of the University of Southampton. We provide cloud-hosted digital archiving and preservation solutions and services. And we serve sectors that already include higher education, research institutions, life sciences, as well as galleries, libraries, archives and museums in the heritage sector. And on the right of this picture are just a few of our customers. And many of our customers already use us for long-term archiving of their research data sets and have been doing so for several years now. This is a really high-level overview of the ARKIVUM solution. So the idea is that content is uploaded and ingested into the solution on the left, which can be various types of content from various sources. And then that content is made available in the future to people who need to use it on the right-hand side. So in between, there's a whole series of workflows, services, and actions that can be performed on content in order to ensure that content remains safe, secure, preserved, and accessible for as long as people need to use it. So I'll be showing you those processes and workflows in detail in this webinar. Typically, we deploy the solution onto cloud infrastructure, so that can be either Google's cloud platform or Amazon's AWS, and we provide a fully managed service. But we can also deploy the solution on-premise if needs be, if there are data sovereignty constraints, or because it makes sense for archive data to be co-located with local facilities and local users. We support a range of standards, certification, quality management, and good practice. So we are certified to ISO 27001 and ISO 9001, and we're audited for both on a regular basis. But our solution also enables our customers to align with standards and good practice. So, for example, the NDSA levels of digital preservation, Digital Preservation Coalition's rapid assessment model for preservation, core trust seal, and FAIR principles for data. And we're actually big fans of maturity and capability models, and we follow them both ourselves and we enable our customers to do likewise. So we can, for example, provide a mapping of all the capabilities and features of ARKIVUMs and products and services, and we can map those to the NDSA preservation levels, DPC RAM, core trust seal, and FAIR metrics. And that helps us show which requirements or levels our solution can enable for our clients. And then in addition to that, all our production software releases are formally validated by an external third-party company, and a validation pack is available that shows that our system does exactly what it's designed to do in a consistent and accurate manner. And we do that primarily because of the requirements of formal software validation for some of our life science customers who have clinical data, where it's a regulatory requirement. But we only have one software product and service that we use for all the markets in which we operate. So validation of software solution benefits all our clients, irrespective of the sector that they might be in. And so that's life sciences and all the rest of our clients too. We provide a range of professional and customer services. So, for example, helping with data migrations or working with third parties on integration of our solution into a wider environment. And we provide a range of educational materials about digital preservation in various industries, including for research data. In ARCHIVER, we've worked really closely with the buyers. So these are the sort of the end user organizations in the project to build a solution that meets the requirements of long-term digital preservation of research data. So through ARKIVUM, we've developed a series of prototype and pilot systems in a very iterative way. But the results of that work has now been productized, and almost everything we've done is already available in our commercial products and services. And crucially, that involves doing a lot of real-world testing at scale and benchmarking our solution to improve its performance, scalability, and cost efficiency. And I'll be talking a bit more about that in a minute when I give you a solution overview. In ARCHIVER, we partnered with Google. They were hugely supportive in the project in their use of their cloud platform, GCP, and that provides compute, storage, and networking infrastructure needed for our ARCHIVER solution to scale to hundreds of terabytes a day for processing and storage. I mean, GCP is already well established in the scientific community for running scientific applications, including at scale with very large data sets. So it's kind of natural for us to extend that into archiving and long-term digital preservation. As well as being very scalable, GCP is well connected to academic networks through national NRENs and through those into Géant. Discounts for educational use of GCP, including egress waivers. And Google, beyond that, has some other very attractive features, for example, their environmental credentials, which I'll cover later. So that's why in ARCHIVER we deployed our solution onto Google's cloud platform, and we're working closely with Google, and we're an official reseller as well. The ARKIVUM solution we developed in ARCHIVER is already available for use. You can find us on the EOSC Marketplace. As well as being able to purchase our solution, we are of course really interested in working with prospective users in further pilots and follow-on projects. And we're really interested in where EOSC will go with long-term digital preservation and trusted digital repository services. And we would welcome working very closely with the EOSC task force on digital preservation on new products and services, or projects and services. So that's sort of 10 minutes on ARKIVUM and who we are and our sort of engagement with ARCHIVER. What I wanted to do next is give you an overview of our solution. So here, I'll talk a bit about long-term digital preservation of research data sets, the architecture of our solution, how we've integrated our solution into sort of a research data management landscape of data repositories and ensuring data is findable, accessible, interoperable, and reusable. So that's fair. Talk a bit about things like single sign-on and how we integrate with EduGain. Scalability and performance is really important in ARCHIVER, so I'll cover that briefly. I'll talk about the different deployment options, both cloud and on-premise. And I wanted to mention a bit about cost efficiency and environmental sustainability. So I'll cover that in the next 20 minutes or so. Oops. So the requirements for archiving and preservation of research data sets in ARCHIVER are being expressed by the buyers in the form of a 4-layer model and a set of use cases. So at the bottom is basic storage for petabytes of data with high-speed ingest and access, and connectivity to Géant networking, as well as basic things like information security. Above that comes the need for preservation services, things like fixity checks, file format identification and normalization, and generally support for things that you would find in preservation standards and good practice. So the things that are talked about in DPC RAM or the NDSA preservation levels. Layer 3 of ARCHIVER includes the ability to search, discover, and access archived data sets, including authentication and authorization of users through federated IAM. So that means things like EduGain. And finally, at layer 4 at the top is the ability to run scientific applications against archived data. And that might be part of scientific reproducibility or simply to enable data reuse. All of that needs to be delivered in a way that meets recognized good practice and standards. That includes archiving and preservation good practice at the lower levels. So following the Open Archive Information System model, DPC RAM and the NDSA levels of preservation. Then comes support for running trusted digital repositories for communities of users, for example, following Core Trust Seal. And then finally, there's the ability to find, access and use archived research data that meets FAIR principles and FAIR metrics. So we've been really careful to develop a solution that aligns with all of those models and good practice. So the end result is a solution that can enable people to build trusted digital repositories for their content in a way that gives them confidence that they're doing things properly. I mean, the desire to follow good practice is one thing. Implementing a certified trusted digital repository is quite another. And FAIR data needs to live within and be accessed from trusted repositories. And users need to know those repositories have maintained authenticity, provenance, and trustworthiness of data that they hold. So this is why we map the capabilities of our solution and our hosted service to assessment models like the NDSA levels and DPC RAM and Core Trust Seal, and more recently, the combined Core Trust Seal and FAIR metrics capability maturity model from the FAIR's FAIR project. So that enables us to make it completely transparent what our solution and services does, including how we can enable organizations to build trusted digital repositories. And I'll show some examples of that a little bit later on. So that allows users of our solution to kind of progress from simple self-assessment and knowing they're on the right path through to formal certification through, for example, Core Trust Seal if we want to. And we're there to help at all stages of that journey. So I should talk more about our actual solution in ARCHIVER. So our approach has been to build a system that operates like a shared factory for use by multiple organizations when preserving and providing access to research data. And that means being able to ingest and preserve lots of different types of data shown on the left, put it through different workflows shown in the middle, and then make it available for people to use on the right. And to extend that sort of factory metaphor, each user of the factory gets their own production lines that can be configured to meet the needs of their specific data and users. Those production lines, if you like, include a set of archiving and preservation services. The bare minimum are shown in green. So this is where our solution does things like basic data checks, generates checksums, identifies file formats, makes copies of data, so replication, and stores them in different locations and does fixity checks. But there are lots more services available in our solution if needed, as shown in yellow. So that includes things like metadata extraction, file format conversions, support for encryption or virus scanning, extraction of data that might be in container formats like tars and zips, indexing and search using metadata, and the ability to sort of package content and export it when needed. And those services can be added into these production lines when needed. And there are detailed mappings that we can provide that show how these set of services enables the requirements of DPC RAM and the NDSA preservation models. So for example, this is just one part of the mapping that we've done to the NDSA levels of preservation. So we've completed the NDSA template, and areas where our solution can fully support the NDSA requirements are shown in green. And then for each area, we provide an explanation of exactly what our solution does and how it meets the NDSA requirements. And we've done a similar thing for DPC RAM, and there's a mapping of our solution to each of the DPC RAM service capabilities. And that includes things like transfer and ingest, bitstream preservation, content preservation, metadata management, and discovery and access. So here's one example for content preservation. And we're quite happy to provide the full mappings to people who want to look at them. And then we take our preservation and archiving solution and embed it into a wider environment that supports construction of trusted digital repositories and support for FAIR principles. So that's what this sort of complicated looking diagram sort of shows. So the core of our solution is in the center, and that's where the archiving and preservation happens. Then we add software for providing additional trusted digital repository services. And in ARCHIVER, we've integrated Invenio RDM to do that. And I'll demonstrate that a bit later on. Then around that comes services for pre and post processing data, both before and after it is archived. So that might be running scientific data applications against archived data sets for reproducibility. And all of that's managed by ARKIVUM and co-located on the same cloud provider. That means that we can provide it all as a single software as a service solution, and it minimizes the need to lift and shift data when it gets accessed and used. And that in turn helps reduce the cost of the solution, both from a monetary and environmental point of view. So to give you one example, here's a data set that was ingested into the ARKIVUM solution, and it can have it's got a landing page that's been automatically created in Invenio RDM, so that data set is discoverable by researchers. So the original data files in the ARKIVUM solution are shown on the left. Those files, along with descriptive metadata, go through all those preservation and archiving services I showed in green and yellow earlier, and then a landing page is created automatically in Invenio RDM, as shown on the right, And that links back to the ARKIVUM solution. So if a user discovers the data set through Invenio RDM, then they can request access to the files or go directly to the files if they want to. And I'll demo that a little bit later on. We've integrated with Invenio RDM in ARCHIVER. We have other institutional repository integrations available as well. So in the past, we've integrated with Figshare and DSpace and ePrints and others, which means that the ARKIVUM solution can be integrated with a sort of repository of choice for a given institution or domain. In ARCHIVER, we're using Invenio RDM. So then it's that combination of archiving and preservation and access through repository front ends that enables us to align well with trusted digital repository standards such as Core Trust Seal. And it enables FAIR principles, for example, easy discovery and access of data sets. So recently, the FAIR project combined Core Trust Seal and FAIR metrics into a single capability maturity model, and we've mapped the ARKIVUM solution to those combined requirements. So it's easy to see how our solution can enable organizations to meet the needs of both. And again, this is just one part of the mapping for one of the Core Trust Seal requirements for data reuse. To make it really easy to use archive data, our solution enables applications in various forms. It could be scripts, virtual machines, Jupyter notebooks, all to be run in the cloud, to be co-located with the archive, and to interact with archive data in our solution. In ARCHIVER, we do that using GCP, so things like Cloud Functions and Cloud Run and Kubernetes. Applications running in the cloud can be triggered by our solution. So they can be, for example, invoked as soon as a data set has been ingested or preserved. And applications can access data and metadata either through our REST API or by exporting it to buckets. And we can expose data through domain-specific mechanisms like xrootd. And that all allows scientific applications to be hosted and co-located with the archive and interact with archive data in various ways. So, for example, in ARCHIVER, CERN have tested that by deploying things like Rihanna and SnakeMake and using those to run scientific analysis workflows that access data that's been archived in our solution. And I'll talk more about that a bit later on. In ARCHIVER, we predominantly deployed into GCP, but the solution is portable to other cloud infrastructures. So we've proven that by deploying onto OpenStack at CERN, and we use AWS for many of our other ARKIVUM clients. And this is all part of ensuring the solution is portable, including features like being able to ingest and export data using native formats and standard protocols. So, for example, all our microservices, the green and yellow things I showed earlier, run in containers, so we can deploy that in Kubernetes in a portable way, so in GCP or AWS or on-premise. And in fact, the whole stack we use for deployment is open source. Google is a sort of exemplar cloud platform, and they've also contributed massively to the open source community through things like Kubernetes, but we're not actually tied to Google. So we can deploy on-premise into private data centers if required. We ensure data can go in and out of our solution using open standards and freely available tools. It could be data transfer tools such as rclone, xrootd, means being able to authenticate with our solution in standard ways, for example, through Edugain, means giving external applications direct access to archive data sets. And it includes the ability to integrate with freely available repository front ends, for example, in Invenio RDM. And data sets can be transferred in and out using open standards such as Baggit and associated tools, for example, to create big data bags. I mentioned Edugain, that's for authentication and authorization. I'll cover this in more detail later, but ARKIVUM is a member of the UK Access Management Federation as a service provider, which means it's possible to log in and use our solution via EduGain Federation, which means institutions can authenticate with their own institutions' services and then be directed to the ARKIVUM solution and sort of logged in using single sign-on. In the last few minutes, I want to talk a bit about scalability and performance, and then cost efficiency and green credentials. So those preservation archiving services in yellow that I talked about earlier, they're all run, yellow and green, they're all run using Kubernetes. That enables us to automatically provision, scale, and use compute resources that match the needs of data sets to be processed. So we can scale the system up when there's lots of data to process, and we can handle hundreds of terabytes a day. But equally, we can scale the whole system back down when there isn't much work to be done. This is just one example. It looks a bit technical, but it's really just a graph of how busy our solution is during a big ingest. So this was ingesting and preserving about 25 terabytes of telescope astronomy images, which were submitted in big data bags inside tar files. And we successfully ingested, stored, and made accessible something like 440,000 images in less than 24 hours. And that includes copying data into the archive, checksum generation, file format identification, metadata indexing, replication to make multiple copies, and fixity checking that that long-term storage was successful. Then when it's all done, system scales back down. And that in turn reduces resource consumption and reduces costs. In some cases, additional processing is required. For example, file format conversions. I'll talk a bit more about that later, but the solution also supports that if needed. So we can convert a wide range of different file formats, images, audio, video, documents, emails, and so on. The system can be configured to follow recognize good practice in that area or domain-specific guidelines for file formats, for example, from NARA. And the system will automatically scale up, apply file format conversions, and we use an extended version of Archivematica to do that. And we can achieve high throughputs that way. So this example shows how we preserved about 50,000 Office documents of various types, including generating PDF-A preservation copies in about 18 hours. Again, resources are only consumed when they're needed to reduce the costs and carbon footprint. So that sort of leads me on to the benefits of cloud deployment, sustainability, and costs. So we deploy our solution into cloud infrastructure, and that's because cloud providers are really efficient in their operations and economically incentivized to do so. So cloud providers such as Google are very energy efficient as well, and they increasingly make use of renewable energy sources. So our whole approach to using auto-scaling serverless computing means that we're efficient in using cloud resources, and cloud providers in turn can optimize our usage of their services in the context of other customers. And the net result overall is less hardware, less power, less carbon footprint, and lower costs for all involved. I mean, I should really make it clear that if we wanted to have a proper discussion on environmental sustainability of long-term digital preservation, we should cover all scope 3 emissions, so things like data center construction and manufacture of ICT equipment. But the data that we have is limited to the carbon emissions that result from energy consumed in order to power the data centers that run digital preservation services. So it's the carbon footprint of that energy consumption that we've been looking at. So in ARCHIVER, use Google Cloud, and you can choose Google data centers that use almost entirely carbon-free energy. And Google already offset any energy from non-renewable sources, so they're already carbon neutral, and they aim to run on carbon-free energy in all their data centers by 2030. And because they provide detailed reporting on costs and resource consumption and carbon footprint, we can compare what happens when users ingest data sets with the consequent costs and carbon footprint, and produce metrics based on real world scenarios that say, well, if you're ingesting this type of data and storing it in this way, or providing this type of access for these types of users, or doing these sorts of preservation activities, then this is how much it will cost per terabyte to ingest, process, and store the data. And this is going to be the likely carbon footprint from a given location where that processing takes place. And that helps us sort of work with customers to minimize both costs and carbon footprint. Okay, so I'm nearly at the end of the overview. Quick summary. So I've shown at a high level how the ARKIVUM solution is very scalable, and it's capable of ingesting and preserving hundreds of terabytes of data a day if necessary. It's possible to co-locate applications alongside archive data. We have integrations with Invenio RDM to make data more discoverable. We have this approach of serverless computing, so only using resources when they're needed, and that makes the solution cost efficient and it minimizes carbon footprint. And we can deploy the solution on various cloud infrastructure as well as on-premise, because we have a solution that's very portable. It's all provided as a fully managed software as a service solution, supports long-term digital preservation requirements, and we can provide mappings to DPC RAM and the NDSA levels, and we can support organizations in building trusted digital repositories and meeting FAIR requirements, and we can provide mappings to Core Trust Seal and FAIR. Right. So that is the end of the sort of overview. What I'm going to do next is provide, so we'll go through part one of a more detailed description and demonstration of the ARKIVUM solution. So that's going to take another 30 minutes or so, and then we'll have a bit of a break. Give chance for people to go get a cup of tea, give me a chance to have a look at some of the questions coming in before we start on the second sort of half of this webinar. Okay, so what I'm going to do is go through several specific things in this first part of a detailed dive into the ARKIVUM solution. So I'll talk about how users can log in, so how they can authenticate and how they be authorized to do specific things. I'll provide an overview of the ARKIVUM web user interface, so what we call the dashboard that we provide. I'll talk a bit about how the solution is configured, and then I'll show how data can actually be ingested. So I'm going to start with authentication and authorization. And we allow, in the ARKIVUM solution, people to log in using either local accounts that are set up or through federation. So the ability to use their own institutions' login services through Edugain. And users can be given different levels of access, so authorization to do different things in our solution. So the different user roles that are available are shown across the top in this picture, and some of the things that users can do in the system are shown down the left-hand side. So administrative users, as you might expect, can log into the system and are authorized to do pretty much everything. But it's possible to restrict access all the way down to what we call read-only users, who can only see a very limited set of content and aren't able to perform actions in the system on that content. And then there are various roles in between. So there's quite a lot of flexibility in terms of the different types of user that can be set up and the different things that they can do. And that extends into what sort of reporting is available to them. So for example, administrative users can have access to full audit trail, but that's not available to read-only users. And we have different workflows that we support. So the ability for ingest to have to go through an approval or approval process before data will be processed by the system. And different users can be allowed to approve or reject things like ingests or deletions or exports of content. So what I want to do now is show that actually working in practice. So this is the first of a series of recorded videos of our solution. I'm going to put all these videos up online and they're full HD recordings. So even if the recording of this webinar doesn't come out very well, then there'll still be these videos that you'll be able to go back to. So I'm going to try playing this one now. In this demonstration, I'm going to show the different ways in which users can log into the ARKIVUM solution, including logging in using local accounts, but also how users can log in through EduGain, which means they can use their institution account and log in using whatever authentication services their institution already provides. I'll talk a bit more about logging in using EduGain in a minute, but first I'm going to log in using a local account. I'm set up in this test system as a full administrator, which means I can see all the data pools in the system. I have access to all administrative functions, and I can see all the data in the archive. And I can perform a full set of actions on that data. So what I'll do now is I'll log out from my administrator local account and I'll log in using an EduGain account. And in this particular test system, it's been set up so I can show EduGain logins through the UK Access Management Federation test identity provider. A where are you from service is also available, so it's possible to look up and find your own institution's authentication service and use that to log into the ARKIVUM solution. And that's possible because ARKIVUM is a registered service provider with the UK Access Management Federation. Here you can see our service in their catalogue and our service entry. And through federation with EduGain, this means people can use their institution's own authentication services when logging into our solution. And the ARKIVUM service complies with the requirements of the Research and Education Federation's Research and Scholarship category. We support Certify, and we're signed up to the GÉANT Data Protection Code of Conduct. To show login through EduGain Federation, I'm going to use two users from the UK Federation's test IDP. One's called Alice and the other one's called Beth. And the difference is that Beth in this example is a member of staff of her institution, and we'll be using that to give Beth different access permissions to Alice. We then configure our solution so different attributes released when a user authenticates with their institution are used to control what they can do. EduGain is just one option for single sign-on, and the solution supports a range of other different options, including be able to log on through social media or... Oops, I'm sorry, I didn't mean to do that. I was clicking on the slide. Sorry, how far do we get? Oh dear, I was trying to increase the volume whilst organizations, authentication services, and now I'm going to log back in as Beth. So I'm back to the authentication page from my institution.
I log in and get taken directly to the ARKIVUM dashboard. And this time, as Beth, I can see a wider range of data pools. I've still got limited administration functions that I can perform, but I can see a wider range of data, and I can perform additional actions on that data because as Beth, I'm a super user. So for example, I'm allowed to bulk export content as well as download individual files. So just to summarize, I've shown in this demonstration how users can log in using either local accounts or through EduGain, so they authenticate with their institution's own authentication services, and how attributes set for those users can be used to control what subsets of data that these users can access in the ARKIVUM solution, and what actions they're allowed to perform on that data.
Right, yeah, apologies for accidentally stopping that video halfway through. I was just trying to fiddle with the audio and make it a bit louder. I was kind of trying to answer questions in the chat at the same time. So hopefully I got back into the video roughly at the right point. If not, then I will make all the videos available online and provide links to them. So you can always go in and listen to them again. Okay. Just to summarize, ARKIVUM, we're a member of the UK Access Management Federation. We're a registered service provider. We're signed up to Research and Scholarship Bundle, Data Protection Code of Conduct, Certify. And that allows users to authenticate with their local authentication services, be directed to our solution, and then attributes that their institution has set for those users can be used to control exactly what those users are allowed to do. In the video I showed eduperson scoped affiliation, but it could be things like eduperson entitlement or other attributes. The point is that this approach of mapping attributes means that an institution using our solution has got full control over who's allowed to log in and what they're allowed to do without involving ARKIVUM to configure the solution or having to do sort of user management in the solution. And I should also say that all the access control that you've seen is also possible through our REST API as well. So to use the API, you need tokens, and those are granted after you log in, and login could be both local or EduGain accounts. Right. So as you saw in the video, when you've logged in, you have access to the ARKIVUM dashboard. So the next demonstration shows some of the different aspects of that dashboard. So let me just see if I can wind the volume up a bit first before I press play, and hopefully that'll be a bit better for people this time.
In this demonstration, I'm going to do a quick tour of the ARKIVUM user interface, so you can see what capabilities are available. The user interface is accessible through a web browser. I'm logged into an ARKIVUM test system. I'm an administrator, so I get access to all the capabilities of the system, and I'll do a quick tour to show you what those are. So this screen shows the ARKIVUM dashboard. I can see the different storage locations that have been set up, how much data is being used in each location, what quota I have, how much data was ingested recently, what processes that data went through when it was ingested and stored and preserved, and I can see when the data was fixity checked, for example, when it was first ingested, or on a regular basis to make sure there's been no data corruption or loss. I can see a breakdown for each of the data pools in the system. So this is how data is partitioned. So I can pick a data pool. I can see how many files there are in that data pool. I can see the data pools that include preservation, those extra normalized versions of my files. For some data pools, it might use different storage locations, for example, deep archiving storage, Because I'm logged in as administrator, I can see how the data pools are configured. I've got control over that, so I can see the different data pools that are set up. I can see the metadata that's supported. So here the system's been configured to support a range of different metadata schemas, including doubling core, ISAT-G, data site, and some specific domain metadata schemas, for example, for some magic telescope data that I've got ingested into the system. I can see what buckets the system's using, which means where I can ingest data from, where I can export data to, and the buckets that are used for long-term storage of data, which could be on fast access storage, or it could be on deep archive storage. Other things I can see in the administrator section, any search queries that I might have saved, and the ability to define different relationships between entities in the system. In the files section of the user interface, I can explore content that's been ingested into the system. So I can see how it's organized hierarchically. For example, allowing me to navigate through data sets and their structure in the files. I can import files as well, so I can navigate through buckets that are used as sources of data for ingest, and I can pick data to bring into the system. And when I do ingest and bring content into the system, I can use the report section to see what's happened. So there's a full audit trail of everything that's done by users and the system. I can see whether retentions or holds have been applied to content. I can get ingest reports on each of the ingests and whether they've been successful or not. Get reports of preservation. For example, this is used to generate additional versions of the content. I can see if data has been exported or if data has been deleted, and I can get details of normalization if preservation has been applied. So as you can see, lots of reporting is available. So when content is ingested, preserved, exported, deleted, and when content is managed in different ways, for example, by applying retention schedules. And everything the system does is recorded in an audit trail. Normally data is ingested into the system using buckets, allowing large volumes of data to be ingested quickly and easily. But if you've only got a few files to ingest, you can do that through the manual ingest feature and drag and drop them directly into the system through the web browser. And then finally, there's a notifications section, so things I need to pay attention to, or notifications when the system has completed different activities. For example, notification telling me that I might need to approve a deletion or an export, or a notification to say that a deletion is completed successfully.
Okie dokie. Oops. In that video, I introduced some terminology, so things like data pools and so on. So I'll talk a little bit about that now. So overall, the dashboard shows you system usage, so data volumes, throughput processes. It allows you to do administration. It allows you to ingest and export content via buckets or through a browser. You can search and navigate. There's a set of reports available. You get notifications when things happen. And because it's all web-based, it's entirely cross-platform. And everything that you see in all of these demonstrations I do, although the demonstrations will be using the user interface, everything is also available through a REST API. So we actually have an API-first approach at ARKIVUM. So first we build capabilities and expose them through a REST API, and then we build a user interface on the top. So in the system, it's possible to configure it in terms of data pools, metadata namespaces, and buckets. So you'll see this in quite a few of the demonstrations. So I'll explain a little bit about what those are now to make it clearer to understand what you see in subsequent demos. So firstly, Data pools, these control the processes that are applied to ingested data. They control who can access data, and they control where data ultimately gets stored. So you might have one data pool where content goes onto archival storage, and that's all that happens, but you might have another data pool where content may also go through a full digital preservation process. So these data pools are where data is stored for the long term. Could be frequent access storage, could be deep archive buckets. Describes what metadata fields and rules should be applied to content that's ingested into those data pools. Describes or determines, data pools determine what processes are run, so which of those sort of green and yellow blocks are applied to content when it's ingested. Data pools include things like whether content is automatically cleaned up, for example, removed from an upload bucket after it's been ingested and stored. Data pools determine whether content's encrypted or not, who can access the content, and there are webhooks available. So when content is ingested into a data pool, then callbacks can be made to external applications to notify them when data has been, for example, successfully ingested. So those applications could then go grab a copy of that data and do something interesting with it, like run scientific analysis. And all of that is self-service. So through the dashboard, you are able to create new data pools, define what type of storage they use, whether they use encryption or not, whether content will go through a preservation process, and so on, and what metadata should be provided or can be provided when content is ingested. Metadata namespaces are about what types of metadata the system supports. So out of the box, we support Dublin Core and ISAG. And ISAG is just an archiving standard from the ICA. So sort of domain independent archiving metadata standards. But you can have domain specific metadata fields as well and set those up in the system as well. So for example, in the case of Invenio RDM, it uses DataCite. So we added support to the ARKIVUM solution for DataCite metadata. So these metadata namespaces, as we call them, enable you to define a set of metadata fields, the types of fields, whether they can have single values or multiple values, whether they need to be grouped together. So for example, you group together might be someone's first name, last name, their ORCID ID, the organization they're affiliated to, and you can repeat that group of fields if you want to for multiple people. And the metadata namespace determines whether the fields are editable or not, so whether you can write metadata once or whether you can update it later. And then finally, buckets are used by the system in multiple ways. They are a source where data can be ingested from. They are a destination where data can be exported to, and they can be used, or they are used by the system, both for temporary and long-term storage. So you can configure the system to use buckets for ingest, storage, and export. Those buckets could be in AWS, GCP, they could be on-premise. Those buckets can have different storage types, so hot and cold storage. Those buckets could be hosted by ARKIVUM as part of the service, or they could be external. We can configure the system so we can automatically clean up content if needed. So if you're ingesting content from a bucket, then when the ingest is complete, then the bucket can be cleaned up. And buckets can be grouped together for long-term storage. So a storage policy might be that you keep one copy of your data on GCP frequent access storage, one copy on GCP deep archive storage to help keep the cost down, and then a third copy might be sent to an independent cloud provider, for example, Azure, into what we call data escrow. So now you've got 3 copies, 2 cloud providers, different tiers of storage, and all of those copies will also be sort of integrity checked. So that enables effective bit preservation to be done by the solution. So you'll see in the demos, I'll talk more about data pools and namespaces and buckets and so on. So hopefully that's given a bit more information on what I mean when I talk about those sort of concepts. The next thing I want to look at in this session, or this part of the session, is how ingest of data sets takes place. So this is getting content into our solution. It's possible to do that via buckets. You can do it directly via our REST API, or for smaller volumes of data, you can ingest through our web user interface. You can do simple things like just ingest a bunch of files. If you want to put files in Baggit bags, then that's fine. We will take those and we will validate the checksum manifest for the bags when the content is ingested to make sure there's been no data corruption. It's possible to put content into archive files, so tar, zips, and so on. And the system can be set to automatically extract the files from those containers when they're ingested. So you can have things like Baggit bags inside tar files and ingest those. And it's optional that you can also include metadata during ingest. For any sort of scale, ingest via buckets is a sort of recommended approach. And we're careful to set the system up so it's sort of cross-platform. So even when using GCP, we'll set up the bucket so you can use things like AWS clients or rClone or other things to upload the data into the buckets. So this is a sort of workflow that happens. You have a data set containing some data files, some metadata files. Those might be in their original native format. And something I'll talk about a little bit later on is a thing that we called Arc Manifest, which is a description of how to process the data set. So how to process the metadata files, where to store the data files, how to structure the data set inside the archive and so on. So a data set consists of these three things. You upload it to a bucket, it's ingested from there into the ARKIVUM solution. It's temporarily stored in a cache where it will be processed. So we can do things like generate checksums and analyze file formats and do file format conversions as necessary. And then it will be stored into different long-term storage locations. And as I've just sort of mentioned, there are different ways of configuring that. So it might be deep archive buckets or frequent access buckets or multiple copies, depending on the value of that data, how often it needs to be accessed, and so on. The thing I should say is that you can do a lot of these things, and the system will do a lot of these things concurrently. So if you're dealing with a lot of data, you can be uploading data sets at the same time as the system is ingesting them, at the same time the system is processing them, and at the same time as it's sort of replicating and storing them. So even though an individual data set goes through a series of steps, as shown here, when you do that concurrently and in parallel for a large number of data sets, then it's possible to get extremely high throughput through the system as a whole. And that's how we achieve sort of hundreds of terabytes a day if needed. So another video for you, which will just show you the ingest process. Make sure I've got the sound up as far as I can. And hit play.
In this demonstration, I'm going to show how data sets can be ingested into the ARKIVUM solution from bucket storage. So here I've got a test system that's been set up to ingest data from GCP buckets, and the GCP bucket contains various data sets. And you can see here I navigate to a particular data set. You can see it contains several folders and files. So we'll be ingesting that into the ARKIVUM solution. So now I go over to the dashboard for the ARKIVUM solution. I go to Files, and then I choose Files to ingest. And that allows me to then choose a bucket to ingest data from, navigate to a data set in that bucket. And you can see here the folders that I showed just now. I can pick that data set and I can say that those files should be imported into the system. And along with the files, it's optional that if you want to, you can import metadata as well. So I'm selecting a file that contains the metadata that describes the structure and the content of the ingest. So now I say which data pool I want that content to be ingested into. So I'm going to pick this data pool here, and then optionally I provide a path within the data pool where I want that data set to go. Click continue. So this is just a summary of the ingest that I'll do, and I click import. You can see here a little dialog popped up to say that ingest has been triggered successfully. I can track the progress of my ingest by going to the ingest report. You can see here the ingest I've just triggered is in progress. And if we wait a minute or two and refresh this page, we can see that the ingest has now completed. So all the files and the metadata have been successfully imported into the system. And now if I go to the File Explorer, I can see the data set that I've ingested, the structure of the data set, and the individual files within the data set. And finally, all actions performed by the system, including ingest, are recorded in the system's audit trail. That includes the original trigger of the ingest and then all the steps that the system took when ingesting the files, processing the metadata, replicating the files to multiple locations, and fixity checking them to make sure that they've been stored successfully.
Okie dokie. So hopefully that gave you an idea of what it's like to ingest content into the ARKIVUM solution. If you're an administrative user or you're given the right to ingest directly, then it's a straightforward process, but it is also possible to configure the system so users are able to sort of upload and request ingested data, but that won't actually happen until an administrative user has gone through a sort of review approval process. So users can upload content, then the system can be set up so members of an approvers group will be notified that there are new data sets available. Those members of the approvers group could review those data sets and decide whether to approve or reject their ingest. If they're approved, the data set then continues through the ingest process, and the decisions on acceptance or rejectance is included in our audit trail, and then users get notifications when their ingests are complete. So ingest can be really simple and self-service, or it can be mediated if needs be. Okie dokie, so that was the end of sort of part one of the three-part detailed description of the ARKIVUM solution. I'm going to propose that we have a sort of a 5-minute break now, just to give people a chance to go get a drink, or maybe if you've got any questions or what you've seen so far, then you're welcome to type those into the Q&A. So I suggest come back in 5 minutes time, and then we'll do the second part of the detailed sort of ARKIVUM overview or description. Thank you. Perfect. Let's go again. Let's share my screen and make sure I'm the next part of the presentation. So solution overview, part 2. So in this part, over the next 30 minutes or so, I'm going to show how it's possible to search and navigate content in the ARKIVUM solution, how it's possible to export both data and metadata if needed, and how it's possible for users to provide and update metadata that describes their content. So I'll start with search and navigation. So it's possible to both browse the hierarchical structure of content in the archive, for example, using a sort of like a tree viewer approach of folders and that's shown on the left-hand side of this picture, but it's also possible to search for content based on metadata to find specific matching files or records or collections or other sort of levels of data. So I'll show you what that looks like in this demonstration. Let's play that and you'll see search and navigation in practice.
In this demonstration, I'm going to show how it's possible to search for content in an ARKIVUM solution using metadata, ways to build up search queries, and then export the files that match the search. The ARKIVUM system I'm using for the demo has been loaded with some astronomy data, so about 35 terabytes of data, just short of 500,000 files. And the data sets that have been ingested include metadata that describe when the astronomy images were captured, which telescopes they were captured from, what regions of the sky those telescopes were pointed to, and so on. So we're going to use that metadata to do some searching. In the ARKIVUM system, it's possible to browse the data sets, so we can see the structure of each one. Each one contains some metadata files and some data files, but it's also possible to search images. So we can do that in several ways. For example, there's a Google-like box that allows simple search expressions to be typed in. So if I look for Perseus, for example, on a search, you can see it's constrained the results to just the files that match my query. So if I pick one of those files and I look at the metadata for it, there's some doubling core metadata for the data set as a whole, and you can see the source field. That's what gave us the match. There's also some telescope-specific metadata that goes into more detail. So the year, the month, the day of when the images were captured, and so on. So now I can use that metadata to filter the results of my search and narrow down to the particular astronomy images that I want. So, for example, I choose a particular year, select the year field. Let's take 2019 in this example. Apply that, and you can see the number of search results has gone down. So I can continue to build up my query to further restrict the results that I'm going to get. So we'll pick the 12th month, so December, and then we'll pick the 31st day. So now we've narrowed the results down to one particular day, and then I'm going to say I want a particular telescope. So I'll choose the M1 telescope in this example. So now the results of my filter search are down to just a handful of files, and I'll pick one of those. If we look at the metadata, we be able to see that it belongs to that particular day, month, and year, and comes from the telescope. Having built up that query, I can save it for future use. So give it a meaningful name, save that query, and that will be added to my list of saved queries. So I can see the ones that I've saved previously, here, and at any point I can then go back to my file explorer and run one of those queries again to get the results. So this query searches for results of the Crab Nebula. You can see the matching files here. Exactly the same idea. I'll switch back to the query I just saved for Perseus. Run that one again, and we'll get back to the results we had just now. I can download individual files if I want to, but I can also choose to export all the files that match my query to an export bucket. So I can give a path in the bucket where I want my export to be placed. I'm going to include both the content of the files and the metadata that goes with them, exported in package format. And the results of my search are now put into the export bucket. So, for example, I could download them from there, or process them, for example, in some sort of scientific analysis application.
Okay, so that's giving you an idea of how it's possible to browse and search for content in the ARKIVUM solution. As you saw, it's possible to structure data sets into a hierarchy, and we do that by using the Portland Common Data Model, so PCDM. So it's a really simple model of being able to say, well, I've got a set of files, they belong to a particular object, it might be a research object, and you can have one or more of those objects that belong to other objects in a sort of hierarchical structure, and those in turn can belong to one or more collections. So that enables data to be organized into data sets, collections of data sets, and you can have multiple hierarchies over the same set of files. So you might organize files into original files or derived files, or into access versions or preservation versions. There's lots of different ways of creating these structures, and then our system allows you to navigate those data set structures. And it's possible to create links between these entities. So we support the data site relation types. It's possible to add other relationship types as well. So you could, for example, say that this set of files is access data versions, and those have been derived from this other set of files, which might be the original data. So you can put these sort of descriptions of how individual files or groups of files or objects or collections are related to each other. When it comes to searching, there's a search box, and it's possible to put search expressions into that box. So Booleans, fuzzy matches, use of wildcards, and so on. As you saw in the demo, there's a query builder, so you can sort of build up queries and filter data sets. It's possible to filter in other ways, so you can filter by which data pools data is in, what type of entity it is, whether it's individual files you're looking for or whole collections. Search results only return things that the user is actually entitled to see. As you saw, it's possible to save and rerun searches, and then the results can be exported. And I'll show a video a bit later on with more details of exporting. Searching can be done through the UI, as I showed, or it can be done through our REST API. And searching behind the scenes, we use Elasticsearch. So it's actually possible to use a full query language for Elasticsearch queries, as well as sort of more simple query strings. If you do find a data set in the solution, say some researchers come along and they've found a data set of interest, or multiple data sets that they want to use, or maybe they've discovered it through a repository front end and they've asked an administrator to give them access. Well, it's then possible to export the files with or without metadata, maybe in a Baggett structure if you want to include checksums. You can export the data set from the system. It can be exported into various buckets. There are webhooks available, so when export is complete, an external application could be triggered, for example, so it can grab that data and start processing it. Exports can go through a sort of request approve workflow, and exports are recorded in an audit trail. So what I'll show in this video is the export process, including, I think, the review approve workflow as an example.
In this demonstration, I'm going to show how a data set can be exported from the ARKIVUM solution into a bucket, so the data in the export can be easily accessed and used. I'm also going to show how exports can go through a review and approve workflow, so that one user might request an export, but that might require an administrative user to approve it before the export will actually take place. So to show that, I've logged into this system as Bob the researcher, and I'm going to go and navigate through the files in this system, find a data set of interest, and then as Bob the researcher, I'm going to request an export of the files in that data set. So I might search or I navigate through the hierarchy of data sets, and here's one that I'm interested in, some data files, metadata files, and then the data set as a whole has got some metadata associated with it as well. So what I want to do is then request an export of that data set so I can access all the files and download them. In this case, I'm going to export just a few files, but in many cases, an export might be terabytes of data or might contain tens or hundreds of thousands of files. Therefore, being able to export the whole data set into a bucket is quite useful because it enables the data to be used, for example, by external applications, for example, for the scientific analysis, or for all the files in the data set to be moved somewhere else, for example, downloaded and processed locally. So what I do is I use the menu option and I request a bulk export of the data set as a whole. So I'm going to say where in the export bucket I want that data set to be placed. I'm going to say I wanted it to include files and metadata, and in fact I want it to include all the technical metadata the system has also extracted for the content. So it's basically everything, all the files, all the metadata, and any extra information that the system has generated as well. So I make that request, and if you notice it said that the request may need approval. Now the system can be set up so no approval is required, and it's simply a case of requesting the export, and then the files will be automatically put into the export bucket. But in this case, I've set it up so Bob the researcher does need approval for his exports to take place. So having requested exports of the data set, I can now go to the reports area of the ARKIVUM dashboard and look at the export reports to see the progress. And you can see here at the top there's the export that I just requested, and it's in a pending state because it's waiting for approval. The export to progress further, what I now need to do is log out as Bob the researcher and log in as an administrative user who has the ability to approve exports. So you can hear I've logged in and I've got a notification that a request for exporting data has been made. So I can review that request, who it's come from, what's been requested to be exported. I can approve that. That approval has gone through successfully, so now the data set will get exported. So if I go to my export reports, I can just wait a second and refresh the page. You'll see that the export is now in progress, so the files are being copied to the export bucket. And I can log out at this point, and I can log back in as Bob the researcher. Bob too goes to the export report and can see that the export is now in progress. When export is finished, the export report will show the success status, which means the files are now ready for access in the export bucket. So if I go here into my bucket browser, refresh the page, I can see a folder has appeared that contains the exported data set. At the very top level of the export is a bagged structure, so that includes a manifest of checksums for all the files in the export. So if I were to download the data set, then I can verify those checksums and make sure there's been no loss of data integrity. And now if I drill down into the data folder of the data set, to the actual files that have been exported. So there's the content files. There were some metadata files as well, original data sets. And then at the top level, there's also an ARC manifest JSON file that contains all the descriptive metadata about the data set. So I can open that manifest JSON file up so we can see the contents, and inside that is all the descriptive metadata for the various levels of the data set that we saw in the ARKIVUM solution. and a whole load of technical metadata that the system also extracted from the files in the data set when they are originally ingested into the ARKIVUM solution. So what I've exported out is all the original files in the data set plus the metadata that describes the data set and the additional information that the system had extracted as well from some of the files. And all those files are within this bagged data structure, including the checksum manifest. So if I do use the files or download them, then I can use the checksums to make sure there's no loss of data integrity in that process.
Okay. So you saw in that demonstration, there was also the export approval workflow. That's optional, but it does mean that it's possible to control access to data. So if a repository does include really large data sets and there would be costs for retrieving it, moving it to buckets and so on, then those could be managed and exports can be reviewed and approved. And that sort of export workflow, including the use of approvals, can actually be combined with some of the integrations we've got. So, for example, with XRootD and Invenio RDM. And I'll show some of those integrations a little bit later on. I now want to talk a bit about metadata. So it's possible to provide metadata to the solution in various ways. You can provide metadata as XML, JSON, or CSV. Those metadata fields are indexed and searchable. We have a way of extracting metadata from domain-specific metadata files. So you can actually map files in native metadata files. You can map those fields to other metadata schemas like Dublin Core or DataSite. It's possible to configure the system with rules that enforce metadata constraints. So you have to have metadata and you have to have certain fields completed and so on. You can provide metadata when data is first ingested, or it can be added afterwards. The metadata can be used to define the structure of data sets. So it's hierarchy, and metadata can be used to link data sets or files to each other. So I'll try and explain how that works. I'm going to use a metadata and dataset example. So this is the data set. On the left, I've got some folders and files. So I've got a folder called metadata, and inside that is some native original metadata for a data set. And that original native metadata is shown on the right-hand side. Happens to be some metadata for a CERN record that they have. And it describes a document in their archive. And that document, I think it's from 1958, and CERN have scanned it. So there's an original TIFF file, and there's also a PDF access version. So that's an original metadata, 2 versions of the file. And then at the top of the data set is the ARKIVUM ARC manifest JSON description of that data set. And that's the thing that tells our system how to deal with that data set when it's ingested. So to try and give you an idea of how that works, this is what that manifest file looks like. So inside, and this is in JSON format, so it's machine readable. So this allows external applications to generate and submit metadata to our solution, as well as people. So you can define the structure of the data set in terms of identifiers, the types of entities, so PCDM collections, objects and files, how they're related to each other using a sort of parent-child structure, and how that relates to the actual files in the ingest and where they're located inside the ingest. So this is how you describe the sort of the tree-like structure that's built up for the data set as a whole. So At the top level, it might be a collection that says, well, here's the data set. Below that, it might be partitioned into, here's the metadata, here's the access versions, here's the original versions, and below that is the individual data files. And in the example, it's really simple because there's only a couple of files and a really simple structure, but this could be quite complex if needed. It's possible to say which files within the data set are native metadata files. So that JSON file that contains CERN's native metadata. So you can say, well, that's where the metadata is. And then it's possible to say how that metadata could be mapped to fields that the system then indexes and makes searchable. So it's possible to say, well, inside the native metadata file, this is where you find the subject, and that should be put in the doubling course subject field in the ARKIVUM system. So you can sort of use JSON path expressions to search within your native metadata files and extract out metadata values and map those to metadata fields in our system. And you can do that for JSON metadata or XML metadata. And at the bottom, it shows how the actual metadata file containing that metadata, where that is in the data set. So the system knows where to find it. And so the metadata can be extracted. And there's the ability to say, well, where in a hierarchy the various data files should sit. So the fact that the PDF file should sit under access data, but the original TIFF file should sit under the original data part of the data set. It's possible to relate different parts of the data set to each other. So you could say the TIFF file is derived, sorry, the PDF file is derived from the TIFF file. And it's possible to say how the individual files need to be stored. So you might say that the original TIFF files aren't going to be accessed frequently, so they can go onto deep archive storage, whereas the PDF file, well, that might just go onto default storage, which could be fast access. So having described all those things in a sort of metadata manifest, the system then ingests the files, ingests the original metadata, does the metadata extraction and mapping, generates this sort of hierarchy for the data set as shown on the left-hand side here, extracts the metadata and maps it. So you can see here the values for title and subject have been extracted and mapped to doubling core, and you can see the relationship between individual files or parts of the data set. So the fact that one file has been derived from another file. It's possible to provide that metadata when content is first ingested, but it's also possible to update metadata afterwards. So you can ingest files and then provide one of these ARC manifest descriptions at a later date. So this little extract on the right-hand side might be describing how to add DataCite metadata to an already ingested data set. And you can do things like export the metadata file that the system already has, update the metadata, re-ingest that back into the system, and then it will apply those updates to the data set or the files within it. Well, that's possible through the UI as well as through the API. As I said, it's possible to extract metadata fields from native metadata files of sort of arbitrary schemas, and through our ability to trigger external scripts and applications through things like webhooks or cloud events, it's possible to add in extra processing of content as well. So it's possible to, say, ingest a bunch of files into a system. When they're ingested, that calls a webhook on an application that does some further processing and then provides some metadata and ingest that back into the system. So there's lots of flexibility. And because there's lots of flexibility, we're able to do complete sort of round tripping and support dataset migrations and exit strategies. So I showed it was possible to export datasets into buckets, including use of Baggit, including the original data files and metadata files. That can include any normalized extra versions of files that the system creates. And the export also includes this ARC manifest JSON description of how that data set is structured. So that means you could ingest data into an ARKIVUM solution and then at a later date export it all again if you wanted to. Maybe that's because you want to move to a different long-term digital preservation system. Maybe it's because you need all that information to do further data analysis. And it's even possible to transfer that content into a different ARKIVUM solution. So what I wanted to do is just demonstrate this idea of data set round tripping by moving data between two ARKIVUM solutions, just to prove that it is actually possible to get everything out of an ARKIVUM solution that was originally put in.
In this demonstration, I'm going to show how it's possible to export both files and metadata from an ARKIVUM solution. And then I'll show how that exported data set can then actually be imported again into a different ARKIVUM system. And I'll use that to show that the exported data set contained all the information on the hierarchy of the data set, the metadata at different levels of the data set, as well as all the files in the data set. And that's important for things like exit strategy, data portability, and basically shows that you can always get out of an ARKIVUM system what you originally put in. So I'm going to start with the ARKIVUM solution used by PIC. You can see here browsing the hierarchy of data sets that PIC have ingested, and I'm going to look at one in particular. So this is some magic telescope data that PIC have ingested, and you can see there are some metadata files, there are some data files. If I view the metadata for a particular file, you can see there's both doubling core and magic telescope specific metadata, and likewise there is metadata for the data set as a whole. So if I look at the metadata, I can see higher level doubling core metadata. So what I'm going to do is I'm going to take that data set and export it into a bucket, so then it can be, well, we can look at the export and then we can import it into another ARKIVUM system and see what happens. So I'm going to bulk export the data set. I'm going to provide a path for where it should go in the export bucket. I can say the export includes both content and metadata. It's in Baggett format, and it should link all the metadata to the files. And I trigger that export. And now the system will put a copy of the metadata and all those files into the export bucket. This is the export bucket in GCP, and we'll wait for the export to complete. And we can do that, track its progress by looking at the export report. It's currently in progress. If we wait for a few minutes, then that will go to success, showing that the files have finished the export process. So export's now completed, and we can go back to the export bucket, refresh the page, and we'll see the exported data set. So there's the folder that I said the export should go into. Inside that is the Baggett data structure. Then there's the actual files that have been exported. So the original data files and original metadata files, they're all in this directory. And then above that is an ARC manifest JSON file that the system has produced that contains a description of how all those files are organized into the data set and all the metadata that belongs to the different levels of the hierarchy and to the individual files. And we can see that JSON metadata here. So it includes the doubling core metadata, the magic telescope metadata, and we've got a hierarchy of entities that describe the data set as a whole and then the individual files. So having exported some files and metadata from one ARKIVUM system into a bucket, we can now go to another ARKIVUM system and try importing that. So this ARKIVUM system here, I've set it up so it has a data pool that matches the one that PIC use for their MAGIC telescope data sets. And that data pool has got a metadata fields defined for it that match those MAGIC telescope metadata fields that we just saw in PIC's data. So here you can see all the MAGIC telescope fields, and those are in addition to the doubling core fields that we support by default. So now we can import the data set. So I go to the import screen, I select the PIC export bucket so I can import it directly from there. There's the data set that I exported. So now I want to import that, and I navigate to the metadata file that was produced when I did the export. And I'm going to put the results into the MAGIC data pool because that supports the right metadata fields. And I'll give it a path of where to put the data within that data pool. And we hit continue and trigger the ingest. We can track the progress of the ingest using the ingest report, and you can see here it's in progress. If I refresh the screen and wait a few minutes, then the ingest will complete. So now that ingest is complete, we can look at the files that have been ingested into the ARKIVUM system. And here at the top is the data set, and you can see the structure exactly as it was in the PIC system. There's the top level of the data set. Below that are the original metadata files from the data set, the original data files. If I pick one of the data files and look at the metadata for it, you can see the doubling core metadata for the file and the MAGIC telescope metadata. So that's all being brought back into the system. If I go to the top level of the data set, then I can look at the metadata for that as well. We can see the original doubling core metadata, the data set as a whole. And then around that is a wrapper that also contains the ArcManifest JSON file that was exported from the original PIC system. So I've got a complete record of the export, and I've recreated the data set in another system, which shows that it's possible to get out of an ARKIVUM system everything that was put in, both files, metadata, and how content is organized into a sort of a hierarchy.
So I kind of labored the point there quite a lot that it's possible to export stuff from our environment without any loss of data, metadata, structure, and so on. I think that's just really important for long-term digital preservation systems, that it really is possible to get everything out that you put in, and to get stuff out in a machine-readable form that can potentially then be moved into other digital preservation environments or used in other ways. Right, so final thing for this part is deletion. So if you do want to, or you do need to delete content in the ARKIVUM solution, and that is possible. It's possible to set things like retention schedules. So you could have a retention rule that says that 10 years after ingest, administrators should be notified because it's potentially the right time to delete data sets. Maybe that's following a funder's policy of retention. Maybe there are other reasons like GDPR and consent and no longer being able to retain data. There could be various reasons why a data set might need to be deleted. So retention schedules can be set up to create deletion events that notifies people to perform deletion. Administrators can go in and delete data sets. The system can be configured so they can delete data sets directly, but what's more common is a deletion approval workflow. So someone can request the deletion of a data set, but it then requires 2 or more other administrators to approve that deletion before the data set is actually physically deleted from the system. So we can configure these sort of workflows. So just in the same way that there's a request approve workflow for ingests and exports, likewise, there is a workflow that can be used to ensure that no one person can go in, delete data sets without approval from other members of an organization. Right, so that's the end of this part, or part 2 of this session. So final part, let me share my screen, I'll share the presentation. So in this section, I'm going to go into a bit of detail about some of the more advanced parts of the solution. So for example, file format normalization, things like being able to control long-term storage, things like replication, tiers of storage, and so on. And then I'll talk about support for fair data and processing data using applications, for example, so co-locating scientific data applications with the ARKIVUM solution. So first up, file format conversions. This is possible in the solution. The solution will identify a wide range of file formats, and we do that using both Apache Ticker to identify things like MIME types of files, but also running file format identification tools that identify files using their pronoun IDs. And then if there are rules in the system that say those file formats can be converted into canonical forms, then it's possible to do that. And we do that by using a digital preservation solution called Archivematica that is embedded into our solution. We run it kind of like a black box in Kubernetes, so we can scale up and run, you know, tens or even hundreds of instances of it to do mass file format conversions. We've extended it so it can do conversions of things like Office formats. So as well as its out-of-the-box conversions of images, audio, video formats, we've extended it so it can convert Office and email formats into things like PDF-A. It will produce both preservation and access versions. And by including that in the solution, it enables organizations to follow recommendations on long-term file formats. So for example, you might be following NARA's recommendation of preferred formats, and hence you might want let's say Microsoft Word formats, old WordPerfect, WordStar documents, etc., to be converted into, say, PDF-A or ODF formats for long-term preservation. So we can configure the ARKIVUM solution to do that by running Archivematica on files and by extending Archivematica to support things like Office documents and email file formats. So this is sort of an example of what that looks like in practice. This is a data set that's been ingested into the ARKIVUM solution. It's got quite a wide range of file formats in it, so documents, PowerPoints, MP3s, and so on. And each of those little colored ovals shows a pair of files. So at the bottom in red, there's a original MP3 file, and that's been converted into a WAV file as a preservation version. In blue is a PowerPoint that's been converted into a PDF, PDF-A actually for preservation. Likewise, green is a docx file, and that's also been converted into PDF. And indeed, even PDFs can be converted into PDF. So if you've got a regular PDF, we can set up the system so that automatically gets converted into PDF-A if needed. So you ingest data into the system, and if you put it through this optional extra preservation process, then the system will automatically generate these extra versions of the files for you. So the process is, file comes in, goes through file format identification. It'll go through metadata extraction to document what it is. If it's in a file format that could be converted, then it'll go through file format normalization. That could also be followed by an optional validation step, for example, checking PDF compliance. Everything is then documented in a METS file, because that's what Archivatica does. And then the original file, the normalized file, and the METS description of everything done, METS and premise description of everything done, then goes in an archive information package, which we then store in multiple locations and do ongoing data checks to make sure it maintains its integrity. As I mentioned, we've extended Archivatica, so not just documents, but also emails. So for example, if you've got a PST file, then we will extract all the emails from the PST, extract the file attachments from the emails, identify the file formats of the attachments. It might be attached images or documents, normalize those, take the EML version of the emails in the PST along with the normalized attachments and the original attachments, and store all those in an archive information package. But we might take the emails and also create PDF versions of the emails and access versions of the attachments and put those in a dissemination information package, so they're easy to use, for example, delivery over the web. So there's quite a sophisticated set of workflows that the system can apply depending on the types of files that are being ingested. And that's all in addition to bit level preservation. So this is how we use multiple buckets for long-term archival storage of content. So this is the workflow I sort of showed earlier, that a data set is uploaded to a bucket, ingested into our solution, and then stored in different long-term storage buckets. And the system can be configured so there are multiple copies of each file. Those copies could be distributed across more than one cloud provider. Those copies can use different tiers of storage. Frequent access or deep archive tiers. We generate multiple checksums for every file that's ingested. So you can see in the sort of top right, files come in and we've generated MD5, SHA 256, 512, and ADLER 32 checksums, and then stored that file in 2 locations. The copies of the files are fixity checked when they're first written to storage. So we'll make sure, using say MD5, that they actually went down into cloud storage properly. And then we'll do ongoing checks to make sure that the copies haven't been corrupted or lost over time. And all of that is recorded in the audit trail of the solution as well. So this is all about sort of bit level preservation and following, for example, the NDSA preservation levels model of multiple copies, multiple locations, different technology stacks, different providers, and ongoing fixity checks. I wanted to demonstrate that process by showing how it's possible to ingest a data set into the solution and say, well, here's some files in the data set that are going to be frequently accessed, so they should go on one set of storage locations. And here's some other files in the data set which aren't going to be frequently accessed, so they should go onto deep archive storage. I've got the volume turned up. Oops, there we go, and we'll play that.
In this demonstration, we're going to be looking at how a data set can be ingested into the ARKIVUM solution in a way that allows some of the files in the data set, for example, the ones that would be frequently accessed, to go onto the one type of storage, whereas other files in the data set, for example, original files or raw data files, to go onto different storage tiers, for example, deep archive, because they're not accessed so often. The ARKIVUM solution uses buckets for data. That includes buckets where data is ingested from, buckets where data can be exported to, and buckets used for long-term storage of data in the archive. So this screen shows the buckets configured for this particular test system, and locations 1, 2, 3, and 4 at the bottom are the buckets used for long-term storage of data, and those are GCP buckets. When data is ingested into the ARKIVUM solution, it goes into one or more data pools, and those data pools can be configured to use different storage locations. So, for example, in this case, I've set up a deep archive data pool which uses storage locations 3 and 4, and those might be, for example, Google Archive tiers of storage, which is suitable for infrequently accessed data. Whereas I've set up another data pool here called frequent access, and that's been configured to use locations 1 and 2, and those might be Google standard or nearline storage, which is more suitable for frequently accessed data. So now let's look at ingesting a data set into the ARKIVUM solution. So here's a data set ready for ingest in a bucket, and the data set consists of files and metadata that are organized into various folders. So in the original scans folder, let's say I've got a TIFF scan of a document. So that's my sort of raw data, if you like, that's not going to be accessed frequently. But in the access copies folder, I've got a PDF version, and that's the version I want to make accessible for people to use. And then finally, in the metadata folder, I've got some descriptive metadata that goes with it, along with an ARC manifest JSON file that describes how that content should be organized when it's ingested into the archive. So if we look at that ARC manifest JSON file, the contents, we can see how that describes the structure of the data set, how those files are arranged into a hierarchy. It describes how metadata should be extracted from the metadata file as part of the data set, and it describes which data pools the files in the data set should be ingested into. So if we go to the bottom of the file, we can see that the TIFF image is going to go into the deep archive data pool, and it will be stored separately from the other files in the data set. Now we go back to the ARKIVUM system, we'll ingest that content. So we go to the import screen, select the data set to be ingested. I'll just navigate and locate it here. So there's the folder containing all those files in the data set. So we want to ingest those. We tell the system where the corresponding ARC manifest JSON file is. It describes how to organize the content when it's ingested and which data pools to use. I'm going to ingest it into the frequent access data pool, which means by default all the files will go there, with the exception of that TIFF file, which I explicitly said in my ARC manifest JSON needed to go into the deep archive data pool. So we've done that, and then we trigger the ingest, and off it goes. So the ingest has been triggered. We'll leave that a couple of minutes, come back, and then we'll look to see the files that have been created in the system as a result of the ingest. So here we can see some data sets that have already ingested into the system. If we go and refresh the page after ingest is completed, we can now see the files that have been ingested, new data set that's created, hierarchy that corresponds to the metadata, and we can go in and look at the individual files. So there were 3 files in the data set. Here's the metadata file. This is the original metadata. Here's the PDF access version, and you can see from the path that it's gone into the frequent access data pool, so it's immediately accessible. And then if we go down to the original data, And we can see here's the TIFF scan, and you can see the path begins with deep archive to show that it's gone into the deep archive data pool, and it's stored in a different storage location to the other files. And we can see the same thing by filtering on the data pools in the system. So if I select just the frequent access data pool, then there's nothing here under the original data, but I can see the access data and the metadata file because they're in the frequent access data pool. If instead I choose the deep archive data pool, then I can see the original data, but I can't see the other files. So that again confirms that the files have gone into different data pools and hence onto different tiers of storage. And that approach can also be used to control who can view and access those files. So users could be set up so certain users could only see the frequent access data, and other users would be able to see the original data files.
Okay. Also remind me at the end to come back and pick up on things like tiered storage, retrieval, latencies, difference between GCP and AWS, etc. I'll put a note down, but that's something there's a few bits of Q&A around that to probably talk about further. Anyway, I wanted now to talk a bit more about the sort of fair aspects of data in the ARKIVUM solution, how it can be made, how data sets can be made sort of more discoverable, publicly accessible, and then how scientific applications can be run against archived data sets. So I showed earlier a screenshot of how you might have a data set in the ARKIVUM solution, but also create a data set landing page in Invenio RDM. So I'll talk you through the workflow for that and then show you a demonstration of how that works in practice. So the idea here is you have a data set. It's got some data files, maybe some original metadata files in a native format. We've got one of our ArcManifest JSON files that maps some of those metadata fields to DataSite, the DataSite schema. And that's important because DataSite is used by Invenio RDM. Ingest the data set into our ARKIVUM solution, and it goes through all the workflows, etc., that I've shown already. But then the key thing here is because it goes into a particular data pool that's been configured to call a webhook, that can then call a service that knows how to take data from the ARKIVUM solution and create records in Invenio RDM. So the ARKIVUM solution calls this record loading service that retrieves the DataSite metadata from our solution, creates a record in Invenio RDM for that data set, so a landing page, and then when it's complete, it makes a little status report back to the ARKIVUM solution so it knows that that landing page has been created. And then a user could go in and review that Invenio RDM record, choose to publish it, which could then in turn mint DOIs and so on. So the key thing here is this sort of idea of a record loading service that mediates the ARKIVUM solution in Invenio RDM, and we call that using webhooks, and it runs in GCP alongside Invenio RDM, and that is kind of like a flexible way to decouple our solution from institutional repository software. So in this case, we're using Invenio RDM. It could be something else. It could be Figshare or DSpace or ePrints or another solution. It's kind of a flexible model. So let me show you what that looks like in practice.
In this demonstration, I'm going to show how a dataset can be ingested into the ARKIVUM solution, and then a dataset landing page can be automatically created for that dataset and published through Invenio RDM. Here's a dataset in someone's data system. It's an example dataset to the ARKIVUM solution. I've got Invenio RDM here. So here's my dashboard. Inside it, there's a couple of applications there. In a bucket, the cloud, I have the data file, data set, and a metadata file to go with it. That's what I'm going to be ingesting into the solution. Metadata file in a minute. Here's the ARKIVUM solution itself. Dashboard. So what I'm going to do, first of all, is just kick off the ingest process, and then we'll go back and look at exactly what I ingested and how the system works. So I go to files, files to import. This gives me a view of the contents in that bucket. So I find my data set, it's this one here. Import the files in that data set. With it. So here's that metadata file. I'm going to put it into a data pool called VM. That's important because anything that goes into that data pool will automatically, well, the metadata will be automatically used to create a corresponding landing page. VM. Folder path. In where it's ingested into the solution. And off we go. So that ingest has been triggered, and the ARKIVUM system is now grabbing those files from the bucket, putting them through our ingest workflow, and when that's complete, a record will be created. So now we can go back and let's have a look at the two files that we're ingesting. So there's a root file, that's the same as the file data set. See here, there's a single file. It's not particularly big, and let's just go through this process. And there's this ARC manifest JSON data file. We'll have a look inside of that. And this is where we've got the descriptive metadata in DataSide format as supported by the ARKIVUM solution. So title and subject, description, one of the creators, data set. There's a data set, there's a couple of identifiers. So it's the record ID and the UI for the data set. So it's a publisher, publication year, and here at the bottom is the actual data file itself, and this is organized into a hierarchy. So that's the contents of the metadata file, and that metadata I just simply took from this record here. So we're essentially going to be replicating this record into just to use the so if we go to the ARKIVUM solution, I've ingested it into the data pool here, and there's a couple of things to note about that. First, it's got a webhook attached to it. So if we just look at the webhook, you can see that when ingest is complete, then the ARKIVUM solution will call this webhook and pass over it the identifier for the ingested data set in the ARKIVUM solution. So this webhook is the little web service that knows how to create records. The other thing about this data pool is that it's set up to support this data site metadata. So it's got these data site namespaces. So if we look at those just briefly, so these are all the different metadata schemas, if you like, that are supported by the solution. Here we allow metadata for data site creators, data site identifiers. So details of these. So here's the data site one. So this is just core data site, publisher, application year, title, subject.
creators, one or more creators with their name and so on. Data site identifiers. So that metadata file here is used to populate these different metadata namespaces in ARCHIVUM when a record is created. So that's probably complete by now. So let's see what's happened. So if I go to my ingest report, how the ingest is completed, success, data set solution. Here we are. So here's the data set. Here's the file. Here's the hierarchy that I defined in the metadata. And here's the data site fields that were in my metadata file. There's the data site metadata. That's the data set. Authors, description, identifiers. So there's a couple of those. There's the identifier. And now that data set's been ingested, again, just refresh this page, you can see that record has been created for the data set. So click on that. So you can see that the title, the author, publication here, description, and then in addition to that, automatically generate a list of all the files in the data set, and then we add that list to the PDF. So there's a little file here called files.txt, and that contains a list of all the files in the data set. I mean, there's only one file in this data set, but the idea. So if there was hundreds of files, then they'd all be listed here. So it's actually in the data set as well as taking up the metadata. And then there are the identifiers. So here is the CERN's record ID identifier. Now, Vimeo RDM supports different types of identifiers, so UIs or arcs or handles. That's the end, but it has a limited set of identifier types. URN is one of them. So I've essentially converted, the software has automatically converted CERN's record ID. Here's the URI that was pulled from the original record. That would obviously need to be updated so it resolves to the RDM record rather than the original portal record. And then finally, related works, there's another URN, and this time it identifies the record or the data set in the ARKIVUM system. So this allows someone who discovers the data set to say, hey, I'd like access to this, and this is the identifier that someone can use to find that record in the ARKIVUM solution. So, for example, take that, I can then go to the ARKIVUM solution, do a search. Record, do that in the tree, so it's the data set in the tree, and I could request for that to be exported, for example, and put into a bucket. When that export process is complete, then the user will be able to access all those files. Finally, remember drawing. So when the record has been created in BNORDM, then a sort of status report is sent back to the archive. And we can see that in the audit trail. If we go to the audit trail, you can see there's some details here of the data set being ingested, it's replicated, fixed and checked. Here's the webhook that was sent off. So it records the URL the webhook is made to, and it records response. I just take that and I'm just going to put that in a tool that makes it a bit easier to see what's come back. So right at the beginning of the record, webhook has been sent to that endpoint, and then it's recorded the response, which is in JSON format. As you can see on the right-hand side, this is now a record of what BNORDM did when it was asked to create the landing page. So it's the metadata that's loaded into BNORDM, and then it was the file that was created with a list of the actual files in the dataset. So that's all included in the archive audit, and that's consistent. So now we've got a complete sort of record of the overall process that was executed. The only other final thing I'd want to say is around identifiers. I've kind of shown how identifiers can be moved over to an BNORDM. In this case, the DOI already existed. If a new record was being created from scratch, then that DOI might not exist, and then in BNORDM would be used to mint a new DOI for that data set. And as I said at the beginning, it might be that a user would go into a BNORDM, maybe they edit this record here, additional metadata they want to put in, or changes they want to make, and then it could be made public by publishing it. That would make it discoverable with a DOI. Users could then see it without having to authenticate.
In this demo.
Okay, so apologies if the sound was a little bit quiet on that. When I put a version up online, I'll wind the volume up a bit higher. I mean, that demonstration sort of went behind the scenes a bit in how that all worked, but I think the important thing is from a sort of user point of view, they create a data set, they submit it to the ARKIVUM solution. Next thing that they see is the landing page being created in BNORDM, and they can go there and they can do any edits and changes and publish it. So from a sort of an end user point of view, it's a pretty straightforward process, although quite a lot of stuff is happening behind the scenes. All that stuff is automated. So next I want to talk a bit about XRootD and making archive content accessible through domain-specific protocols. So in this demonstration, I'm going to show how a data set can be ingested into the ARKIVUM solution and made available through an XRootD server. Let's make sure the volume's up as high as it will go.
Demonstration data set can be exported from the ARKIVUM solution in a way that allows that data set to be accessed and used through XRootD. For example, so it's easy to use that data in scientific application. So this diagram shows the overall workflow that's supported by the solution. The idea is that a data set files and some metadata ingested into the ARKIVUM solution storage safeguarding. And I suppose at some later date, someone wants to access and use that data set. They might go directly to the ARKIVUM solution and find it by searching the metadata,
or they might have discovered the data set through some external application, for example, Convenio RDM, shows how we integrate that. Either way, the user comes on to the archive solution and they find the data set and they want it to be exported so it's accessible through. Make a request to the archiving solution for the data set to be exported. At that point, it might be that that request needs to be approved, and we do have a workflow in the archiving solution that allows an administrator to approve requests for data set exports. In this demo, I'm going to show the data set being exported directly without the process. That is possible if it's needed. What then happens is the data set is exported into storage underneath an X-Root D server. And the way that we do that is archive export buckets. So we make the storage underneath an X-Root D server file system look like object storage by using Minio, and that means we can export directly to it. And when the data set is then passed through Minio onto the file server, it can be accessed through the X-Root server. So let me show you that process itself. So I'll switch over to the archive dashboard. File Explorer, see some data sets that are already installation. And here's one that I'm going to use for demonstrating export. It's actually quite a small data set. Inside here, there's a single file. So to export the data set, I go to the menu and I say export all the files of the data set. And there's only one in this case, but it could be hundreds of. Now I'm going to export it into this particular bucket, and that's the one that's connected to the X-Root server. In this case, I'm just going to export the contents of the files themselves. I could also, if I wanted to, export the metadata that goes with those files. Metadata. And I could export it in Baggett format, so complete with checksums, etc. But in this case, I'm just going to export the files. Let me give it a name that's useful, so we'll be able to find it easily on the X-Root server. So let's just use the so I made that export request. That's triggered the process in the archiving solution. Report exports. So you can see this particular export is in progress. It's going to take a little while to complete, and when it does, I get a notification it's done. So we'll let that run, and then we'll come back to the server. The X-Root D server itself, I'm going to access it on the command line. So let's just have a look at what's in there at the moment. So I'm going to use the XVFS command line to just list the contents on the X-Root D server. So you can see there's a couple of data sets that are already there, but not the one that I've just exported. So I'm going to have to wait a little while, and when that's complete, we'll come back and you can see the contents of the data set through X-Root D. Server. Now if we go back to the command line, you can see here that data set is there now. You can see then the path of the files. Make the data pool of the file, then the data set. exported. There you are. There's the actual details. That's a pretty straightforward process. So essentially on demand, either a user or administrator can go to the archive solution, search and find data sets, and choose for them to be exported, and that export can be directly to an XRP service that can be accessed by external applications.
Cool. It's not particularly exciting trying to demonstrate X-root-D, but the whole point is that you can get stuff out of the ARKIVUM solution and make it accessible through different protocols, so it's immediately usable by different sort of applications. I expect to use data that way. And that's all part of enabling processing of archive research data sets in the cloud, so co-locating applications with archive data. We do that in GCP by allowing applications to be run, for example, as cloud functions or in containers using Cloud Run or using Kubernetes or even as some virtual machines. Those applications can be triggered, so invoked when data is ingested, preserved or exported. Those applications can use our REST API to do searches, get metadata, get hold of files. And as I've just shown, there's the X-root-D server that enables them to access data through different protocols, such as X-root-D if they don't want to read it from buckets. So those sort of webhooks I mentioned, they can be set per job. So each time you do an ingest or request preservation or do an export, you can provide a webhook that says what application to invoke. Webhooks can be run by default for a given data pool, so always called when an ingest is completed, and they can be secured. So you can call, the system can call secured external applications. So for example, CERN have been trying this all out. So they've been deploying scientific applications using frameworks such as Rihanna and Snakebait, and using that to do sort of rerunning scientific analysis on CERN open data sets that have been archived into our solution and then made accessible through X-root-D. So it's a really minor configuration change. So these tools just point to the X-root-D server that we host in GCP. Tools run in GCP, and then they produce exactly the same results that they would do if they were run locally at CERN. So all of that really is kind of enabling more than just digital preservation of research data, but making research data discoverable and reusable. And together that means that we sort of support this sort of whole stack of things like bit level preservation through to content preservation, through to building trusted digital repositories, through to ensuring data is findable, accessible, interoperable and reusable. So, just a reminder that is described, for example, in the self-assessment that we've done against the recent combined core trust seal and fair capability maturity model. That includes what's supported by our core solution, what's supported by additional things like Invenio RDM. So it's completely clear on what part of the solution is enabling what core trust seal or fair metric to be supported. Okay, so I'm pretty much at the end. Just a couple of things before we wrap up. Of course, I'm happy to take questions. There's a range of further materials. So I did quite a rapid overview of what the solution can do. We of course provide further materials like a user guide, API guide. In ARCHIVER, we developed a series of what's called cookbooks that are how to use specific features, including sort of examples of how to invoke them using the API or command line or through the web UI. We're happy to do further demos or get involved in pilot projects. For people who become clients for ARKIVUM. They go through a proper onboarding process that includes detailed training, so a lot more substantial and sort of more hands-on than the things that I've shown today. That's all supported by a Zendesk support portal that we run, which provides access to documentation and training materials. As I said, we can provide mappings to the NDSA preservation levels, DPC RAM, core, trust, seal, and fair metrics to provide people with a better understanding of what our solution can do. And they're, for example, building trusted digital repositories. If you're interested in some of the performance scalability aspects of our solution, then there's a paper I published and presented at IPRES last year. And we've also got an IPRES panel on ARCHIVER coming up later on this year. And finally, because ARCHIVER is a European Commission supported project, it produces loads of deliverables. So there's lots of further content that's available through those. And some of them will be made publicly accessible over the coming month or so through the ARCHIVER project. So just to wrap things up, so hopefully I've shown you how the ARKIVUM solution enables long-term digital preservation of research data by going through processes of ingest, preservation, safeguarded, so about long-term storage, the ability to search and navigate and find content, the ability to export content, the ability to create landing pages and so on. I've shown a little bit of how we can support reuse of data sets, for example, by making it accessible through XRootD, making data sets discoverable through Invenio RDM, and be able to connect to various applications that can run in the cloud and be co-located with scientific data sets in our archiving solution. We've deployed into GCP and ARCHIVER. We deploy onto AWS often for many of our production customers. And in ARCHIVER, we showed how it's possible to deploy our solution on-premise using OpenStack. It supports authentication and authorization to control who can access the data, what they can do, and so on. And that includes using an institution's own authentication services through the EduGain Federation and allowing the institution to directly control which of their users can use the ARKIVUM solution and what they can do. I've mentioned repeatedly that we're here to try and support good practice assessment and certification from a digital preservation, trusted repository and fair perspective. And we provide mappings for those. And the solution I presented is available for use today. We are listed, for example, on the EOSC Marketplace. We are more than happy for people to contact us directly. Or if you're, for example, you're already a Google user, then you can contact Google and work through them to add our solution to what you already use. So with that, I'd say, yeah, well, thank you very much for sticking with me for the last 2 and a bit hours. Hopefully that was informative. I've tried to answer as many questions as I could as I went through. And I'm happy to take more questions now. I'll stop sharing my screen for a moment. There we go. Right, so I'm just looking through some of the questions at the moment. Yeah, some of those further materials, yes, we can make them available. So for example, if you want to get in touch, then we can provide them to you if you want to, for example, look at our user guide or delve into our API in more detail. Some of those materials are available as part of onboarding. So when customers actually start using our solution and we take them through detailed training. And some of the materials, things like IPRES publications and archive deliverables, yes, they'll be public and you can either access them already or you'll be able to download them soon. Yeah, and apologies, it was a long and hectic webinar. Yeah, I covered quite a lot of content quite quickly. I mean, this has been recorded, so you can go back through it, and a lot of the videos that I showed, we'll get them up online. I'll increase the volume a bit where I can. So if you do want to go back and see what I actually did and demonstrated and take it a bit more slowly, then that's possible too. Anyone else got any questions or comments or thoughts? Licensing. Yeah, so licensing is an interesting one. So the solution is provided software as a service. So something that we host and manage typically in the cloud, say GCP or AWS. So you would use that on a subscription basis. So there will be an annual fee for us providing the managed service and the software. And there is a charge that is dependent on the amount of data being stored in the solution. So obviously, the more data you ingest and the more you store, then the more the costs of doing that in GCP or AWS go up. So we have a per terabyte sort of pricing model. So you can say, well, I've got this much data, and then we price it up in terms of an annual management fee plus a per terabyte charge for ingesting and storing and accessing that data. In terms of the actual software itself, some of it is obviously ARKIVUM proprietary software, and other parts of it are open source and freely available. So it's a bit of a mix in the sense that a lot of it is open source and portable, and that enables us to deploy into different cloud providers or on-premise. But the ARKIVUM software application itself is ARKIVUM's proprietary code, and that isn't open sourced. We, of course, license it on a subscription basis. So using ARKIVUM and Google AWS via Okra, and what happens next? Yes, I think that will be possible. We need to work out the details. So whether it's someone who's on the existing Okra framework as a reseller who would then resell our solution with, say, GCP as a cloud platform, that will be possible. I don't know exactly what's going to happen to Okra next. There's also the EOSC Marketplace, and that enables you to find that you can either buy directly from us or you could go to Google, and it's also tied into the various, or the best way to handle things like discounts, egress, waivers, combine the ARKIVUM solution with maybe other uses you might already have for GCP. So I think I'd say that we are flexible. For example, you could come to us directly. We are a Google reseller, so we could provide a complete hosted solution that bundles our software and Google's infrastructure. We would be perfectly open if you've already got using Google directly, that we could deploy our solution that uses infrastructure services that you are purchasing from Google directly. So then we just charge like the management fee, or we'd be quite happy to work with other resellers and provide our solution that way. And I think there's quite a lot of options. So if you want to explore those in more detail with us, please do get in touch. Okay, I'm not seeing any more questions coming in at the moment. So I'm happy to conclude
Matthew,
the webinar.
I don't know, I think there are a couple of questions more in the Q&A.
Oh, okay, hang on. Yes.
I think you have not answered them, or I missed
Yep,
it.
quite right. Thank you for pointing that out. So question about ARKIVUM going through upgrades, software improvement versions. We tend to release new versions of our software solution every 3 to 4 months. Each production release goes through this full computer system validation process. Those releases already include almost everything we've done in ARCHIVER so far. So ARCHIVER itself is essentially an R&D project to develop new solutions for long-term digital preservation that work at scale. As we've been doing that through phases 1, 2, and 3, we've productized the results, and that's already available in our commercial solution. As we come to the end of phase 3, we're completing that process. So 6.0.0 is our current software version. We've got another one coming out in a couple of months' time, and by the end of the year, I'd imagine everything done in ARCHIVER will be fully available in our commercial offering, including being validated, etc., by third party. So on-premise installations. So we would still provide a managed service even though the solution is deployed on-premise. So we would, a client would provide us with access to their on-premise infrastructure. We would go in and deploy the solution, monitor it, manage it, deal with upgrades and so on. And we would charge for that service. But obviously the underlying compute storage resources used by the solution would be provided by the institution, and that's not something we'd obviously charge for. So that's why we sort of split out this software licensing management sort of fee from the underlying costs of using infrastructure to process, store, and provide access to content. Again, we're more than happy to explore the models for that if you want to get in touch directly. Cool. Anything else I missed?
No, I think no.
Brilliant. Yeah, sorry I missed those. I was looking in the chat, not the Q&A.
No problem.
If anyone else has got any sort of follow-up questions or things that come to mind, yeah, please don't hesitate to get in touch. Always really interested to hear suggestions, comments, receive questions, have discussions on our solution, how it might be used, how it could be deployed, and so on.
Thank you very much, Matthew, for this very interesting webinar. I think there is some questions more. I think maybe we have. No. So thank you very much to all the attendees for joining this webinar. I think this was very nice, and we will be sharing the recording with all the participants. And yes, so we hope to see you soon in the next events of ARCHIVER.
Great. Thanks to everyone for attending. Hopefully
Yes.
it was useful.
Okay, I think we have all the question addressed now. And compliments to you, Matthew, for the presentation. So thank you very much for us, I mean, from us as well. And see you soon. A good day to you all.
Likewise. Thank you very much all.
Bye.
Bye.
Thank you very much.